All right, welcome ladies and gentlemen. This is video number 3 in our organic notes on homologous series and isomers. We need our notes open to page 9 for this, and we will also need our reference tables. Open up to table Q for this video. So please make sure your notes are on page 9, that you have your reference table open to table Q. So in this video, we're going to be talking about homologous series and isomers and essentially defining both of these terms. Homologous series. You'll notice that that's the title of table Q. We've already been working with table Q, but we haven't talked about what that word homologous means. Well, it has a prefix that we have seen before, homo, and we know that the prefix homo means the same. So a homologous series is essentially, if we look at this definition, it's a group of compounds that are all the same as one another. They're not necessarily identical, but in terms of organic chemistry, they all belong to the same group of compounds. Meaning, you have, let's say, 3 compounds and they're all alkanes. That would be a homologous series. Or you have 3 compounds and they're all alkenes. That would be a homologous series. Or if you have 3 compounds and they're all alkynes, that's a homologous series. So homologous series is simply saying, hey, they're compounds that are all alkanes, or they're all alkenes, or they're all alkynes. They can be have different numbers of carbons, but the bonding will be the same in each of them. So that's why the title of table Q is homologous series of hydrocarbons. We have alkanes, alkenes, and alkynes. Now, we also have 2 types of hydrocarbons. We have saturated hydrocarbons and we have unsaturated hydrocarbons. We've seen the term saturated and unsaturated before. Saturated meaning full, unsaturated meaning not yet full. A saturated hydrocarbon is by definition an alkane. Meaning a saturated hydrocarbon contains all single bonds between the carbon atoms. So the helpful way to remember this little mnemonic device is saturated starts with S, single bond starts with S. So saturated hydrocarbon contains all single bonds, saturated single bonds. Now, what is it full with? Like, why is it called saturated if it's all single bonds? It's full with hydrogens. You can't fit any more hydrogens on it. So it's saturated with H's. There's no more H's that could fit onto the carbon chain. Saturated single bonds, those are alkanes. An unsaturated hydrocarbon is simply not a carbon that contains all single bonds. So unsaturated would mean, if we have unsaturated, it would mean that we would have a double or a triple bond in our carbon chain. So alkenes are considered unsaturated hydrocarbons and alkynes are considered unsaturated hydrocarbons. It's unsaturated, meaning it's not yet full, because you could fit more hydrogens on. It's not yet full with hydrogens. It would be possible to add more hydrogens onto that carbon chain if you took away the double or the triple bond and you made it a single bond instead. So using this, and tables P and Q, we can name these compounds and determine their homologous series and work out if they're saturated or unsaturated. In doing this, though, we want to use the general formula that's on table Q. So the general formula for an alkane, as you see, is CnH2n plus 2. The general formula for an alkene is CnH2n, and an alkyne is CnH2n minus 2. So in looking at these compounds that are in this table, all we've been given is the formula. So work out the pattern. And the first thing you want to do is figure out, like here, C3H8, which formula, the CnH2n plus 2, CnH2n, or CnH2n minus 2 it fits into. Well, if it has 3 carbons, and then you double it, you get 6. But then if you add 2 more, you get 2. So this is the general pattern of CnH2n plus 2. So if it's that general pattern, then the next thing I'm actually going to fill in is the homologous series. Because if it's that general pattern, then I know it's an alkane. And if I know it's an alkane, then it has to be saturated by definition. I'll do the names last for each one. So we'll look at the next one, the C7H12. Well, the N is 7 because there are 7 carbons. If I double that, that's 14. But then if you subtract 2, that's 12. So this fits the general pattern CnH2n minus 2, which, filling in the homologous series next, is the general pattern of an alkyne, which by definition is unsaturated. And the last one, C5H10, N is 5, so CN, but then if you double it, you get 10, and that's all it is. So this is simply CnH2n. So based on the fact that it fits that pattern, it's an alkene, which by definition is also unsaturated. Now, in terms of naming these compounds, what I'm going to do is I'm going to take the suffix from the homologous series and make it the suffix for the compound. I know that if it's an alkane, it's going to end in ane. And then in terms of filling in the prefix, I'm simply going to look at the number of carbon atoms and use the appropriate prefix for that number of carbon atoms. So if there are 3 carbons, the prefix is prop. So therefore, the entire name is propane. The next one, if there are 7 carbons, the prefix for 7 is hept. So 7 carbons, but it's an alkyne, it's going to simply be heptyne. And the last one, the prefix for 5 carbons is pent. So I know the entire name is going to be pentene. So that's how you can simply look at an equation. You don't even need to see the bonding of a hydrocarbon in order to work out the correct name for the compound. Isomers. Isomers are based on a prefix that we have seen before, iso. And iso, where we saw this with isotope, iso means in chemistry same but different. It means that there's something the same between these two compounds, but there's also something big that's different between them. So an isomer in organic chemistry is a compound. They're compounds, so you need 2 of them. They have the same molecular formula, but different structural formulas. So they have the same number and type of atoms. So they have the exact same number of carbons, exact same number of hydrogens. But they have different arrangements of the atoms. They have different bonding of the atoms. So for example, if we look at CCCCl, and we do that versus CCCCl, if I look at these 2 compounds here and I tally up, each of them has 3 carbons, 7 hydrogens, and 1 chlorine. So we fit this definition. They have the same number and type of atom, 3 carbons, 7 hydrogens, 1 chlorine. But notice that in this one, the chlorine is on carbon number 2, and in this one, the chlorine is on carbon number 1. Yes, it's on the first carbon, because remember, you number your carbon chain so that your substituents are closest to the number 1 carbon. So the bonding is different. And that's an isomer. Same number and type of atoms, different arrangement of those atoms, different bonding of those atoms. Now, the key thing with isomers is that if they have different bonding, they will also have different physical and chemical properties. As soon as you change the bonding, as soon as you change the arrangement of atoms, you will change the properties of the compound. So isomers, although they have the same type and number of atoms, they will have different melting points. They will have different boiling points. They will have different medicinal properties. So this example, this table that you have, we have 2 compounds, ethyl alcohol and dimethyl ether. Notice that they have identical numbers and types of atoms, C2H6O. They each have 2 carbons, 6 hydrogens, 1 oxygen. But then if we look at the bonding here and here, location of that oxygen is different. So the arrangement of the atoms is different. These are isomers. They have the same number and type of atoms, but different arrangement of those atoms. When we then look at their properties, notice we have very different boiling points, very different melting points, and in terms of physiological activity, meaning the effect on the body, ethyl alcohol is a depressant, so it puts you down. It kind of knocks you out, well, not knocks you out, but makes you tired, makes you sleepy. And then we have, on the other hand, we have diethyl ether, which is an anesthetic. These are completely different properties, so they affect the body in very, very different ways. So different arrangement of atoms, different properties. So an example of a question with isomers, draw all of the possible structural isomers for C4H10. Well, there's always one way that we can arrange atoms, and that is in a straight line. So this is always kind of the easy way. meaning I can take these 4 carbons and just put them all in a row and then fill in the 10 H's. So this is one possible arrangement of the 4 carbon 10 hydrogen combo, but then I want to do another arrangement. So now I want to think about a branched structure, meaning substituents. You have substituents. So this one would have 4 carbon chain. In order to have a branched arrangement, I can no longer have my longest chain being 4 carbons. So now I think about maybe having a 3 carbon chain. So doing maybe 1, 2, 3 like that, and then making a 1 carbon substituent. Now I would have to put that not on the ends, because if I put it on the end, right, if I put the C here, then my longest carbon chain is still, you know, there. It's still 4. So that's no good. So I have to put my branch in the middle. I have to put it in the middle, otherwise it simply becomes part of the longest chain. And I could then simply fill in the hydrogens. I still have 10 hydrogens, but I have this distinction between what's the longest carbon chain and are there any substituents. So these are actually the only 2 isomers for C4H10. There's only 2 ways that you can arrange that. Quick comment about isomers and names. An easy way to check to see if these 2 compounds are in fact isomers for one another, or if they're simply the same compound, the exact same compound, drawn a slightly different way, is to name them. If the name of the 2 compounds is different, if you're following all the naming rules and you get different names and you have the same number and type of atoms, then you know you have isomers. But if they have the same name, then they're just the same compound. So that's a quick sort of check, like name them and see. So an example of how the Regents will try to trick you with isomer questions is shown here, and they'll give you this compound shown here, and they'll say which of the following was an isomer for this compound. My recommendation is to start by, first of all, examining the compound that you've been given at the top of the problem and working out how many carbons, how many hydrogens, how many other atoms. So this compound has 3 carbons, it has 7 hydrogens, and it has 1 bromine. Your answer must have those number of atoms. If there's a different number of atoms, then it's not an isomer. So start by just tallying that up. The next thing I recommend doing is name this. The name for this compound is going to be 1,1-bromo-propane, right? And we're going to use that because that's going to help us evaluate these other options. So looking at choice A, it has the correct number of atoms, meaning it's the same number of atoms as our one that's shown above, but this is still 1-bromo-propane. So this is not an isomer. It's the same exact compound. An isomer has to have a different structure, a different bonding, a different arrangement of atoms. This has the exact same arrangement of atoms. So what? Who cares? You drew the bromine going down instead of going to the left. It's still 1-bromo-propane. So it is not this option. The next one is not going to be an isomer because there are too many bromines. Right? This compound contains 2 bromine atoms. We are only allowed to have 1 bromine atom. So it does not have the same number of atoms, so that is not an isomer. Choice C is really the one that's going to, I think, trick you the most, because you look at it and you say it has the exact same number of atoms, and the bromine is on a different side of the compound. It's 3-bromopropane. There is no such thing as 3-bromopropane. Remember, you number your carbon chain so that your substituent, which in this case is the bromine, is closest to the number 1 carbon. This is still 1-bromopropane. They just wrote it with the number 1. Basically, they numbered their carbon chain right to left instead of left to right. So it is not this option, and that's the big way that the Regents will try to trick you. We look at the last option. It has the correct number of atoms. It has 3 C's, 7 H's, 1 Br, but the bromine is on the number 2 carbon. So this is 2-bromopropane. Not 1-bromopropane. It's a different arrangement. The bromine is in a different location. It's bonded to a different atom. So this one is the isomer. Same number and type of atoms, but a different bonding, a different arrangement. There's a reading that's on pages 11 to 13 in your notes on properties of hydrocarbons in a distillation review. I would love it for you to answer those questions. It's not a necessity, but it would be helpful for you to get that done prior to class tomorrow. If not, I do expect you to work on that in class tomorrow, in addition to the problem sets you're going to have on isomers and homologous series.